Hi there. We're going to present today our final project for Math 214. It's going to be on image processing. So the goal of our project was to take digital images that are represented by matrices and decompose them using singular value decomposition, and then augment the eigenbasis of those images to essentially reduce their dimension and prepare them for more computational heavy algorithms. So the singular value decomposition, which is the linear algebra procedure that we're going to be heavily using here, is a process by which we take a matrix and we break it down into the U, S, and V components, the U component being a square orthogonal m by m matrix, the S component being a diagonal matrix with singular values along the diagonal, and the V matrix, which is transposed, being an m by n matrix. And then we can look at those singular values. The largest ones are the ones that correspond to the greatest scalar multiplication of those two square matrices. And the smallest ones are closer to the kernel. And we can remove the smaller singular values to augment the matrix, the original matrix. Then we can reconstruct it and we'll have a new matrix. You can see below in figure 2 that what it looks like when we reconstruct and decompose these matrices. Currently in this figure 2, you can see that we kept two singular values in our S matrix. You can see they're both very large. The other ones would have been much smaller. Those two singular values would then be used to reconstruct the image matrix with only two components, lending to a much smaller size matrix and smaller dimension matrix. And I'll pass it along to Trent now for the data set and procedure.
All right, we'll be using the MNIST data set and augmenting it to demonstrate the application of our program. You can see it below in figure 3 that it's a collection of handwritten numbers, 0 through 9. And this is just a small part of it, and it contains a lot more. And yeah, each of these is different handwritten. And we choose this data set because we wanted a grayscale image rather than an RGB image, because it's easier to deal with one set rather than an RGB with 3 matrices. Right. And now we move over to the procedure and results. So after importing the images, we use the SVD function through NumPy to decompose each image from our data set into square orthogonal matrices under the influence of singular value scalars via the singular value decomposition. And after eliminating the non-essential values, we can reconstruct the images to see how many singular values are necessary for recognition by our algorithm. Below, you can see several examples of this process in figure 4. And we can see that below 4 components or singular values, it's pretty hard to distinguish what the number is, and it's hard for the program or algorithm to distinguish it as well. But when we use 4 or 10, as in the last column to the right, they become pretty crisp and recognizable. And yeah, to reiterate, we found that 4 components was the smallest number for acceptable results to be recognizable. And this is backed by this scatter plot here. And really the scatter plot can only show it in 3 dimensions because it's hard to make a 4-dimensional scatter plot that the algorithm could recognize and cluster together these different numbers, which just shows that it can designate and recognize them independently. Now I'll pass it off to Noah to discuss the code.
All right, thank you, Trent. So the code for this project was very simple because we were able to utilize the NumPy library in Python, which already has a single value decomposition built in as a function. So in the code, you can see that really there's 4 main parts. There's transforming our image into the U, S, and V matrices, and then reconstructing the image using the number of components we want to use. From there, we're able to print what the original matrix looked like, what the reconstructed image looked like, and also create the scatter plot that you see that basically classifies each image as a set of its 3 largest components, because anything greater would be too hard to visualize on a plot. So we're really only able to visualize up to 3 components. And yeah, I'm going to pass it on to Hassan for the conclusion.
Okay, so to sum it all up, we used SVD to deconstruct non-square image matrices and remove the lowest singular value while keeping the original image mostly intact. We saw under procedure and results in figure 4 that the more components we use, the greater the clarity of the compressed image, but that would increase the information that we need to store for reconstruction. So we need to find a perfect middle, where in our case, it was 4 components. Anything less than that would not be clear enough for the algorithm to recognize again. And anything more could be too redundant in terms of efficient computation, at least. All of this was done in Python, and we gave an example of a deconstructed image in our math section. So using the deconstructed images that we obtain through this method, our data becomes ready to be used in more complex computation-heavy algorithms, such as the classification algorithm that we mentioned. And that pretty much sums up our project. Thank you all for listening.